Yo, it's good. So we're gonna be speed running more chemical kinetic questions. So yeah, we'll just get into it right now. So I realized that like Loki, it might be illegal what I'm doing. So I don't know. I have to like think of some new questions. So yeah, I'm kind of cooked in that part. But anyways, um, so in this question, we know that half-life decreases as we continue on, and it's said to be 10, 20, and then 40 minutes, where A naught equals 0.1 moles per liter. Now the calculation is, what is the concentration of A after 25 minutes? So we got to figure that out. So the first thing that we need to find out is, what order is this reaction? And I just realized I don't have the formula sheet open right now. But what order is the reaction? Well, if we know that the successive half-lives are decreasing, it cannot be first order, right? Because for a first order, T 1 over 2 is equal to ln 2 over K. And these two values are like not based on concentration. So successive half-lives are going to stay the same for that said reaction, so it can't be first order. Second order, 1 over K A naught. So what we're saying is that the half-life, wait, hold on, no, they increase, wait, my bad. They increase. Half-lives are increasing, right? So as the reaction proceeds, if half-lives are increasing and the concentration is decreasing, half-life increasing and concentration is decreasing, therefore these should have a inverse relationship to each other. So that means it must be second order, because a zero order is T1 over 2 equals A naught over 2K. So T1 over 2 and A naught, these have a direct proportion to each other. So as half-life goes up, then, as concentration is higher, goes higher, the half-life increases. But that's not what we're looking at right now. We're looking at half-lives are increasing while concentration is decreasing as the reaction proceeds. So therefore it has to be second order reaction. So I'm just going to get rid of all of this. Oh wait, that's low-key one other thing that we need. 25 minutes. So we know that this is going to be a second order reaction now. Now we can simply fit this into our integrated rate law for the second order. So this is going to be 1 over AT equals KT plus 1 over A naught. Okay, so what's K? Oh, we don't have K. We have to find that out. Bruh, that's low-key annoying. Okay, well, I think we know how to do this. Second order, T1 over 2 equals 1 over K A naught. And we know that the first half-life is 10 minutes. So that means we could just do T1 over 2 multiplied by A naught to the power of -1 is equal to K, because we have to do the reciprocal to find K. So what is... Am I missing something? T1 over 2. So half-life... That means... what? So we start with 0.1. T1 over 2, that's going to be 10 minutes. Multiplied by A naught, which is 0.1 molar. And I'll put it to the power of -1. So that would be 1 to the negative... Wait, what? 10 times 0.1 is 1. 1 to the power of -1 is 1. So that means it'll just be 1 moles per liter, -1 min, -1. But I feel kind of sussed out like that. That's all I have to sub in, because we're not even talking about what the concentration is. But I guess that's all we have to do. Okay, so we found K. Now what do we need to do? We just have to solve for what is it? Concentration at 25 minutes. So times T 25. Just put this all to the power of -1. So it should be 1/25. Or no, wait, I forgot the last part. Plus 1/0.1. Okay, wait. Let me just redo this part again. Loki kinda boring, bro. Okay, so 25 plus 1 divided by 0.1. Zero point 0.0286. There you go. That's the answer. Question 2. Hopefully I can get all this done, bro. I don't care, bro. I'll just do this like that. This is low-key sus if I just don't do anything. Well, I'm upstairs. A reaction is carried out at 25 degrees Celsius. When the temperature is increased by 15 degrees, the rate doubles. What is the activation of the energy? Blah, 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 blah. I don't know. Okay, so we're going to use this equation, I believe. K2 divided by K1 is equal to EA over R, 1 over T1 minus 1 over T2. Okay, so T1 equals 25 degrees Celsius. T2 equals, what's 25 plus 15? 40 degrees Celsius. K1, we could say it equals 2. K2, we could say equals 4, because 2 times 2 is 4. We could say any number for K1, and then all we need to do for K2 is just double it. Now we need to find EA. What is that equal to? We'll find out. So ln 2, because 4 divided by 2 is 2, is equal to EA over R, and I believe we have to do this in Kelvin, if I'm not mistaken. Ah, yeah, we do. Broke. 298.15 Kelvin minus 1 over 313.15 Kelvin. What's the value of R? Whoops. Shoot. Where's the value of G, bro? Oh, R. Wait, R? When do we use R? Why are we using R? I guess we are. Wait, what? Oh, 8.314 joules mole per Kelvin or whatever. That's low-key weird. I did not expect that. Okay, let me just find out what this value is. Whoa, that's a weird number, man. EA, bro. EA. Now we're just solving for EA. Just need to figure out the most efficient way to do this. Yeah, what if I just do 1 divided by this? I think that's easier. 8.314 multiplied by ln of 2 multiplied by 6224.36. This is equal to 35.87 times 10 to the 1, 2, 3, 4. 1, 2, 3, 3. So then we could say this as kilojoules. 36 kilojoules. There you go. That's our answer. Next question. No, I forgot to make a new page. Oh, there you go. Fast. Okay, I low-key don't know how this one's gonna work. For a given reaction, the rate constant K was measured at 2 different temperatures. The 2 data points were determined in this experiment as follows. The student who performed the experiment applied a logarithmic linearized form of the Arrhenius equation. What value of EA did the student get from the experimental data? What is the value of A? What is the value of A? What even is the value of A though? What is the order of this reaction? What are we even trying to solve for A? Huh? How do we do this? Okay, the linearized form of the Arrhenius equation. What even is that? Yo, I don't understand why we don't use the rate constant K was measured at 2 different temperatures. The 2 data points determined in this experiment are as follows. So is this 1.1 times 10 to the negative 5 minutes to the negative 1 the rate constant? I don't know. It's a good question, bro. I don't know how to do this, bro. What? Why don't we just use this equation, bruv? Why don't we just use this equation, bruv? I don't know. I feel like I should ask ChatGPT this. What? Because we have T2, we have T1. The rate constant K, we got that as well. I'm very curious now. I mean, I guess it says logarithmic, but the other one has a log as well. You know what? I'm going to try doing it this way and then see how that goes. Okay. I mean, I guess that we need to find ln of A. So then I guess we could infer that we have to use the other formula, but why, bro? But why? But why? Why do we need to do that? You know what? We'll just not do this question right now. Yeah, I don't think we're going to do this question right now. Yeah, I'll just figure this out on my own. I really don't know what I'm doing here. Let's move on to the next after a short water break. Now we're getting into showing that a right law is consistent with whatever we found. Let's figure this out. I low-key forgot how to do this as well. This is not very good looks. Okay, even when a mechanism is consistent with the rate law, later work may show it to be incorrect. Okay, la. Show that this mechanism is consistent with the rate law. Okay, so we need to determine the rate determining step. That's the first step, I remember. Rate determining step, that's what will determine overall K, the overall reaction, if you will. So RDS, that's the rate determining step. What is that going to be? That's going to be the slow step. And in that case, it'll be reaction 3. So we're going to write out the rate law for reaction 3. Rate equals K3, remember reactants, there we are. Now, we need to have the original, okay, wait, but let me just write this. Bro, can this not work? Okay, we need to get the original overall reaction. That's what we're trying to capture, right? But right now, as you can see, we have neither. Oh no, we have I. Oh yeah, we have I. So we have I, but we need to get rid of H2I because as you can see from the overall, we don't have H2I. H2I is an intermediate. So we need to get rid of it. So it's just a process of elimination by combining the other things with it as well. So how do we eliminate H2I? Well, that's a good question, bro. I really don't know. It's going to be K2. Okay, I'll just actually label this. K2, K minus 2, that, the other ones. Okay, now what do we have to do? We have to get this K negative. We have to get this H2I out. Which other equation has H2I? Well, reaction 2 has it. So we're going to have to use reaction 2 to eliminate H2I. How do we do this? That's a good question, bro. Let me figure this out. Okay, so K2. So the rate of a fast equilibrium will, like the forward and backwards will equal each other. So we could just say the rate forward is equal to rate backwards. So yeah, K2 H2 I is equal to K minus 2 H2I. So we're trying to solve for H2I. That means we just need to rearrange it so that we could put whatever is on the left side into the H2I portion, kind of, if you see what I mean. There you go. So now we have H2I right here, and we could just substitute this in right here. Does that make sense? I hope it does. Rate equals K3 times K2 over K minus 2 multiplied by H2 multiplied by I multiplied by I. Now, do you see I2 and I? These do not equal each other, so we need to replace I now. How do we replace I? Well, I hope you guessed it right. We're going to be using the equation 1. So we'll just label this K1, K minus 1. So K1 I2 is equal to K minus 1 I squared. Don't forget that because we got a coefficient there. Almost forgot that. So now we need to replace I. Well, K1 over K minus 1 I2 square root is equal to I. 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 Oh, wait, we don't need the square root. Because I times I is just I squared. So we have I squared here. Now we're just going to put this in right here. There you go. That actually makes so much more sense. I was low-key concerned because I didn't see a square root in the answer. There you go. Is that right? Yeah, that's right. So then this is the right law. Damn, bro, I'm low-key kind of lost, bro. I'm not fully confident in this. Okay, 2 more questions and then we're done. I'm so tired, bro. 7:41 already, bro. I got an econ midterm tomorrow. Dude, I'm so cooked, bro. It's not even funny, bro. Okay, let me try doing this quicker. Following okay, whatever. So the issue is here that we don't know which one's fast, which one's slow, and which one's slow. So we don't know what the RDS is. RDS equals question mark. What is the slow step here? Well, if we look at these, right? This is pretty big looking, like K1. This is pretty big. This is also pretty big. This is definitely the slow step. This is significantly smaller. So K2 is going to be the small one. Reaction 2. Hello. Reaction 2. So now let's just write out the, we need to determine the, what is the overall reaction? Bro, we gotta figure that out too, bro. No. Bro, brother. I think it's the best to just find out the overall reaction so we know what we're trying to get first. So we're gonna try doing that. Oh my god, bro. Okay. What even is the overall reaction, bro? Oh. 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 Bro, am I even doing this right, bro? What? Brother. Yeah, let's just do this. Okay, Cl2. Okay, I might get this wrong because I'm trying to do this like off my head. There you go. I think this is right. So that means OVR. So what we're trying to obtain is rate equals Cl2, CHCl3. That should be what we're trying to get. So then the rest will be intermediates. Okay, so now RDS rate CL3 K2. So we can't leave this. We need to get CL out. How do we get CL out? Well, we got to use we just use step 1. Why am I tweaking over that one? Okay, so K1 squared. Yes, sir. Okay, so now we're gonna have to square root both sides because we don't have a CL squared in the equation. What am I even doing, bro? I'm just tweaking, bro. C1 over K2 CL2 square root. Substitute that into here. Wait, where did I even get this K minus 2? Isn't this going to be K minus 1, bro? Oh, well, I'm actually asleep, bro. CL2. Bro, why does it look so complicated? Okay, is that all we need? CL2. Oh, wait, this is all we have to do. Oh, wow. Okay, so this is the overall. Now we need to find the rate law and the magnitude of K. So that's a good question, bruv. Okay, well, let's see here. You got 1 and wait, we're not even looking at this. We got 1 over 2 and then we got 1. So we should have a 3 over 2 order. So now in order to find whatever K is, K overall is equal to this. So that means it's equal to K2 1.3 times 10 to the negative 2 multiplied by 4.8 times 10 to the 3 over 3.6 times 10 to the 3. Now what will we get? Bro, I'm so done with this, bro. Actually, bro, I low-key am going too slow for Chem 102, bro. I got my final, what day? Next Wednesday? Today's Thursday? Oh, yeah, bro, I gotta lock in this weekend, bro. But I'm low-key, bro, this is my worst, like, part, so I think I'm chill. I've been taking finals way too light, bro. I've been saying that everything is tankable, but in reality, nothing is really tankable. Nothing's funny right now. Okay, 0.015. Okay, so it's 3 over 2 order, so 3 over 2 minus 1 equals 1 over 2, so negative 1 over 2, so that means it should be negative 1. Yeah, that's the answer. Okay, last one. Almost there. Oh man, this is a freaking steady state approximation BS, bro. Okay, that took some time actually. This is gonna take low-key long. Okay, let me cook on this one, bro. We got this one, bro. This shit's light, bro. It's not even hard. Okay, so this one issue is we don't know which one is fast. Fast? I don't know. RDS? I don't know. So we gotta find that out. How do we find that out? I don't know, bro. I don't know. Oh, actually no. We assume that the RDS is the one that makes the products. First of all, just to make things easier, let me make the overall reaction. 2NO plus Br2 becomes NOBr2 gets used, 2NOBr. So that means overall our rate law would be K multiplied by NO squared over Br. Wait, what am I even doing? Okay, wait, we don't even need this, bro. I don't think so. We just need this, bro. That's all we need. Okay, so what do we do now? I don't know. Let me look at this. Okay, so we're gonna assume that RDS is what we're looking for. I mean, RDS is the second equation equation. So this is like 2, this is 1. So we're going to assume that RDS is the second one. So that means rate equals K2 multiplied by NOBR2 multiplied by NO. So now NO is good, but we don't want this. So we need to find a way to substitute NOBR2. So how are we going to do this? Using steady state approximation. We don't know which one is bigger, we don't know which one's faster, which one's slower. So we're just going to do steady state approximation. What does steady state approximation mean? Well, it means that the rate of formation of intermediate equals the rate of disappearance of intermediate. So what does this mean? Well, what reactions are forming the intermediate NOBR2? Well, K1 is. So K1 NO, because this is going to equal the rate, yeah? So BR2, that's the only one that's forming NOBR2. Oh, no, there's the other one, yeah. Wait, no, there's only one. Forming. Yeah, forming, okay. Now, what is the ones that are disappearing it? K negative 1, NOBR2, and K2, NOBR2 times NO. There you go. So now, we have to isolate for NOBR2. That seems like a bit of an issue. What? Yeah, okay. So K1 NOBR2 is equal to NOBR2 multiplied by K negative 1 plus K2 NO. So now, what is NOBR2? BR2, we isolate it, yada yada yada. K1 NO BR2 over K negative 1 plus K2 NO. Okay, now we have this one and we just put it in right to here. Mink. So rate equals K2 K1 NO. Okay, so we got 1 NO here and we got 1 NO here, so it's going to be NO squared BR2 over K negative 1 plus K2 NO. Yes, nice. Okay, so that's the rate. So now, what do we have to do? Derive a theoretical rate law for the above mechanism. Okay, so I think here we have to, like, I don't know, we have an addition thing on the bottom, so we can't, like, fully assume that, I guess. So we have to narrow it down into, narrow down to extreme condition. What are these extreme conditions, you may ask? That's a good question. I don't know. I used to know. Oh, I think we just use the ones that are in the denominator. So K negative 1 and K2. These are the two things we're going to be comparing. So first we're going to assume when K negative 1 is greater than K2, which means that K2 is like not occurring. You know what I'm saying? So if K2 does not occur, this is going to be 0. So therefore the rate is going to be equal to K2 Wait, if K2 is nothing, then why would... What? So we're going to assume that K2 is slow. So that means... Assume it's like 1, 0. But we don't take away the other K2. I don't know. We're just going to keep on going with what we have. I should probably watch the video. So yeah, so what we're going to be left with is a 1, 2, 3 order reaction. This is a third order. So now the other thing that we're going to assume is K negative 1 is just simply the opposite. It's smaller than That means k negative 1 is slow. That means we're just going to have the same thing. So it'll be a second order then. Because if k negative 1 is slow, that means we're going to cancel this one out. Wait, no, not that one. Cancel this one out. So then we're going to have 3 over 1 equals 2. So second order. Okay, yeah, there you go. That's all, bro. That's all. Bro, that was actually bad, bro. I'll see you later. Goodbye.